But this works very nicely for the conceptualized models. So now, this is again the video of the snap-off process. And what's happening here now, the oil, the brine is not, or the water is not shown. You see the water is pushing the oil and is cutting off here. The same story is happening here, is layers of swelling in the throat until it just snaps off here. It cuts this. And this happens within fractions of seconds, like less than 1/1000th of the second. So we can't record this because our imaging speed is about 38 seconds here. So what we can do as the data, so what the first thing we did with that, we can convert water-oil interfaces into a curvature mapping. If we can get the curvatures from Young-Laplace equation, simple equation, if we know the surface interfacial tension, we can get the local capillary pressure here. So it can give us the information, quite a lot of information about the pressure, but it's computationally very expensive to calculate these things. So what do we get here? So this is a lot of, sorry about the busy slide, but I'll only won't explain a lot of things, but only a couple of major points here. So let's say this is my oil moving and snapping off here. I make a line, I call this ganglion side, and this is connected side. Now what I can do, I can calculate the capillary pressure here and here. And in water-wet system, what's happening? The capillary pressure is dropping with time as you inject water. And keep in mind, capillary pressure in general is a pressure of oil minus pressure of water. If this pressure is decreasing, that means my water pressure is increasing. Okay? So which makes sense, because if you're injecting water, pressure has to increase. So this pressure is decreasing, capillary pressure is decreasing both sides the same way. But at some point, let's say at point B, there's a disparity in pressure. So what we have, this pressure drops significantly. And this pressure drops, and this matches very nicely with this data set here. When you have plot the saturation, let's say I'm only going to focus on the throat here, and there's empty symbols which represent the volume into throat. And you see at point B, it drops significantly. So what's happening here, if you look into the zoom image of the throat, yellow is my oil and blue is my water. And with time, you see the water layers are swelling, exactly like in the same cartoon I showed. So the water layer is swelling, and this represents the oil shrinkage here, is exactly the same thing, is opposite in this way. And then at that certain pressure, you get the disequilibrium and it cuts it off. And what we also found that during this pressure disequilibrium, and if we call it event here, when the disparity starts, the whole event takes about 15 minutes. So when we looked into many different ganglia, it took about 11 to 15 minutes. So this was quite new information because we want to model something, but this wasn't expected here. And also we are not clear about what's the effect of flow rate on this event size. So we're going to explore this in the future. Okay, so this is one example how the pressure disequilibrium, because of pore geometry, I'm going to explain you why it happens, how the layer can flow and snap off into the pool. And it gives, small subset gives quite a lot of information, but we have big data set to explore. And now, let's say I will go one step back. I say, okay, I want to explain this snap off, not in terms of curvature and a lot of expensive calculations. I want to explain everything based on geometry. Can I do that? So I represent the whole system. Let's say this is a small subset of my data. This is the pore space, which is semi-transparent. I convert into pore and throat network. What it means, let's say this is a cartoon of my pore and throat space again. And as I said before, throat is the minimum constriction. I can put maximum sphere, which fits into the pore space. And then I can connect them with a tube, which has the same radius as the throat. So this is how we make the pore and throat network. And this 3D is exactly the same situation here. And now what we have the oil. We can put the oil on the top of it. And now we know where the oil is moving. Now we can characterize what pore and throat space is invading and where it's getting trapped. So we did two different analyses on it. One, we calculate the aspect ratios. What it means here, so let's say my interface moves from this pore to the next pore. It's called the pore filling event. Water is invading, pushing the oil into the next pore. if I take the ratio of this radius to this throat, I call this aspect ratio of my event. And if you calculate the events, there are 8 events. If I look into the aspect ratios, they range from 1.2 to 2.1, where there's no snap off. But where the snap off occurs, aspect ratio is 3. It's quite high. This goes nicely with theories because mostly we have got cartoon or conceptual framework, and we can calculate those pressures where we say it's about 2. And this is the first time we can prove the same thing. Even in complex geometry, we have something very same sort of thresholds here. Second thing, what we want to do is calculate the shape factor of throat. There's a formula here. Generally, traditionally, it's done area over perimeter square. But here, because we want to take care of the roughness, I won't go into too much of details. We're using something very simple formula as well. So what we want to do, I calculate with the same formula, simple formula, the shape factor. I'll explain you what it means physically in a second. So I look into the shape factor where the things move. It's only the shape factor of throat. And I compare, it ranges from this number to that. But with the snap off occurs, the shape factor is on the smaller side, which works very well because if you have smaller shape factor, that means you have more corners. Okay, this just explains this way. If you have more corners, you can have more water present in the system as a layer, and the layer can glow and can snap off things. It just explains this thing. Nicely works. So we wanted to do the whole thing in the whole system, not on the small subset. So we expanded it, but we had to simplify the system in terms of pore filling mechanisms. So what it means by pore filling mechanisms, so let's say this is my configuration of fluid. This is 1 pore, 2 pore. It's all filled with oil, and then rest is water. I call this I1 event because one throat is full of oil here. I call I3 event because it's 3 throats are filled with oil. Okay, so this is simple IN mechanisms. I won't go into details, but mostly what you can think about, if I calculate the pressure, so it's I1 is for the same pore size, I1 is easier to invade compared to I3. So what's going to happen? I1 is going to move this way. Let's say my water pressure increasing. It can move this way, yes. Or, as I explained you in the previous slide, the layer can grow in the throat and can snap off. So there are 2 competitions going on. Either it's going to pore filling or snap off. And I did the whole thing on the same complete data set and looked into the histogram of aspect ratios where we didn't have the snap off. And we see mostly everything happens below, let's say 1.5. And we looked into all the snap off, it happens at 2.1. So this is very nice. I was very happy to see the correlation here. And this I didn't expect very well in the complex rock system here. But when we looked into the shape factors, without trapping, as a histogram again of the shape factor, it ranges, which is fine. But when I looked into snap off, it again ranges same spans. Although 70% they lie below into smaller values, which makes sense. But we still have quite a lot on the larger scale. So my thinking would be probably is the resolution issue. We can't really resolve the throats very well to calculate this shape factor because it's a very complicated structure. But maybe there's some physical aspects which I might be missing. So I'm looking into detail here. But I was super happy to see this, that at least this correlation works very nicely with the aspect ratios here. Now what we can do, one thing can snap. We have trapping because of snap off, but we can have trapping because of bypassing as well. And you see a lot of larger droplets, ganglion, because they have bypassing. What we're having here is, so let's say this is the oil, and then it gets cut here. When I looked at the aspect ratio, it didn't fit very well. That means snap off doesn't occur. So now only 2 cases can occur. Either it do pore filling into this pore or this pore. If I look into sizes, my interpretation, it goes from here. Once it goes here, then I make I1 event, it just flows there. So this pore filling can lead to the bypassing of this ganglion. And we are now trying to calculate and analyze the data same way for the whole data set with the terms of aspect ratios and other factors as well. But this is just to give a picture of the I2 event is an I2 event, also how it can lead to the trapping of the oil. Now there's some unexpected things happening in the pore space, so it's really important to discuss those as well. For example, this is my I2. I2 means 2 throats are filled with oil, and interface moves from one time step from here to there. And if I look at the aspect ratios, they are quite high. It should snap off here, it should trap here, but doesn't trap. I only found only one event in the whole tomograms of 400 images. So what we're trying to do, we said, okay, we need to do simulations. So simulation not only for validation, we would like to learn something from there. So very nicely, there's a very smart gentleman. He's a postdoc at Imperial. So he did simulations. First, we gave him very test cases where snap-off occurs, pore filling occurs, without telling him that we're expecting this. And then he came up with this simulation, and yeah, said it doesn't trap. Or we were super like on the cloud, but we still don't know the answer yet. Because we have got this analysis done a week and a half ago, but I think what we're planning to do is look into the localized curvatures, pore geometries, what exactly is leading to. Although it's only one event and 400 images, I would like to know why it happens. Second one thing which we didn't know about is, let's say this is my I1 event. Oil is sitting in this throat, and I'm pushing the surface interface. In the next step, it doesn't snap off big, it doesn't completely wash it away, it just sticks on the side. Now, for oil industry, it might not be very important because it's a very small, tiny droplet. I found 3 to 4 events in the whole image. But if you're thinking about contaminants, you want to remove those contaminants, you would like to know it, how they get trapped. Then we think about and where they get trapped, right? So this was a very interesting case. Then we gave to the same guy to do simulations. So this is another case, but same story. It goes, next step, leaves behind tiny droplet on the side. So we want to do simulation. Let's say we are doing simulation with the 45 contact angle, and the interface moves, and we don't see trapping. And this is not explaining what we are having here. Then we discussed quite a lot on this, and then we came up with the idea, maybe the roughness is quite high here. If you have high roughness, as I shown in my second slide, it can change the contact angle. The contact line can increase your contact angle there while movement. Okay? So this is what we thought, okay, let's try this. We put all the contact angles down 45, except a patch where we saw the more roughnesses, and we knew it. I know it's a little bit tough, like we knew it, that this is trapping here. We just changed the contact angle there. We made it, let's say, 60. Oh, it didn't change. So we were a little bit disappointed again. Then let's say maybe the roughness is increasing because we don't have information about that 1C contact angle. So that's what our plan is, to do the 1C contact angles. So now we do it 70. Yeah, here we go. So it taps there, right? And then we said, okay, let's play with 90. And we played 90. It works. The size increases. So what we will look into now, looking into between these transitions here. And we'll try to match with the sizes. And also, the idea would be to learn the physics, what exactly is happening here. So this was interesting. We were really, really happy that something is working on the based on simple principle, changing the contact angle, things like this. This is just to show an example. Let's say you have trapped everything. As I said initially, trapping in the water wet system, if you keep flowing under the same condition, it will never mobilize because of capillary forces. But you can increase the flow. So this is just a normalized saturation. Let's say you're looking into sandstones. I'm plotting it against capillary number here. What is the function of velocity, viscosity divided by interfacial tension here? Okay. So I increase the velocity. The saturation decreases. Okay. This is expected. But then there was a nice paper looked into what exactly is happening at the pore space. The oil can not only mobilize, let's say oil is sitting here, it can not only mobilize, but it can really fragment into smaller pores, the droplets. And we wanted to see, okay, let's say we increase the velocity. Now, instead of velocity, what we do, we change the surface tension, right, or interfacial tension. Let's say while mixing, what we can do, we can mix soap, or we use chemicals. And let's say this is my oil sitting in the pore space, and we see the same sort of things, right? So this is interesting to see the mechanisms that are happening at pore scale. We haven't explored this yet. This was just a curiosity experiment we did with the water wet system. Okay, now, so far we've looked into water wet system. And the reality is, if they're looking into crude oil system, they go quite complex. And I'll explain in the next few slides later the mixed variability, how it can change things. and how it's rated, why is important. But let's make the system a little bit simple. We use spherical particles, and we fill the whole system with oil. Now I do inject water from the base, and then image at the synchrotron, but this time with a speed of 1.4 to 2 seconds, very high speed there. And then look into what's the displacement mechanism. The only thing what I change between experiments is the contact angle throughout the system. I change from 20 to 160. So there's a range of contact angles I'm using here. So this is an example with 75 to 125 contact angle. And you can see here is a vertical cross section of the sample. Black is oil, full of oil. And then I start injecting water from the base. And under this condition, you see it makes quite flat front, leaving behind nothing. And now you see with the 125 contact angle, it makes jumps, ramified finger formations. And this is the same story here with the 3D images. And what you see, different colors, they're different time steps. So you can see a lot of finger formation, ramification of the front. And you see the jumps as well, like in drainage process. As you can see here, like this is plotted the front area or the interfacial area. As you can expect here, you have more finger formation, you'll have more area here. This is exactly what it's saying. It's more area in this case compared to this with time. But you see the saturation of oil, as you expect, because it's a flat front, it will get to the final saturation very easily. So that's what we see. It just comes to the saturation here. But in this case, it takes quite a lot of volume of water. Okay, so with time flushing, what's happening actually here? If you look into the 75, it's all 75. Now I don't show the water phase, I show the oil phase. So see, you see the oil yellow, and this is the disconnected oil. The oil is moving, leaving behind some sort of trapped oil there. And within one pore volume, small fraction of water, it traps things. But in this case, you still see after 10 pore volume, so quite a lot of water, the things are connected. Yellow is connected, it traps. That means it's making all the finger, layers of oil, they drain slowly with time. You keep injecting, but you can also see, if you are like thinking from the oil industry point of view, it's a lot of water injection. It's not very economical in this case. This is probably the highlight of this study is plotting contact angle and versus the saturation, final saturation. Again, you see the saturation doesn't change for the lower contact angle, but then there's a threshold, then it changes completely. And it doesn't happen 90, it happened between 90 and 100, 110. So this is interesting because we can't expect a layer flow like this in this region here. The same thing what we got, different saturation in 2D system, but same trend here. But this is like a very uniform system. Same size of glass beads or any spherical particles. But if you increase slightly complexity, you mix the two different sizes, you see the heterogeneity in this system, you don't see the flat front. You don't see the same thing again. And if you use sand under the same contact angle, you see the trapping, more trapping. That means it's not only wettability, but also you have the roughness, you have the angularity of the pore space. This can give even the system, even water wet system, more complex. We also did some curiosity basic, like mixing different contact angles and looking into, as expected with 75, it just likes this, like this. And when the water pressure increases, then it starts invading the other things. But it's the same story in the other side, but it's slightly difficult to say because it's mixture of two different sphere particles. But if we look in 3D system, so this is 75 contact angle, this is 125. You see all the oil is sticking to this oil wet surfaces, which makes sense. And here is the same story. I removed the blue color, but it's sticking to the other surfaces. So this, we didn't publish this thing, but just our curiosity, if you make layers and if you mix the beads, what happens? But now, coming to the slightly more complex system, it's a mixed wet system. Why it's important? Let's say your oil is formed in a source rock. Once it's formed, let's say due to buoyancy, due to gravity, it moves to the current reservoirs. The reservoirs, initially they are water wet.